Okay, hello to everybody. This is the fourth lecture on this series of lectures on matrix algebra, and today I want to speak about some property of the inverse matrices and something about the idempotent matrices. Okay, last time in the lecture 3 I've not mentioned that why it is useful, this inverse matrix. Why? Because if we have a matrix A that is a m by n, then exists a unique matrix that we can call A inverse that is also m by n, such that A multiplied by A inverse is equal to A inverse multiplied by A that is equal to the identity matrix. And this is the real definition of an inverse matrix. And other facts that are important on inverse matrices is that if we have, for example, A that is a m by n, and we multiply by B that is a m by n, and we want to take the inverse of this product, then this is equal to the B inverse multiplied by A inverse. Then we exchange the terms when we want to take the inverse of the product. Then the inverse of a product is the product of the inverse of the second element by the inverse of the first element. And this is a very useful property that maybe it's useful when we invert matrices in the regression model. And useful facts that we can see about the invertibility of a matrix are this one, that A that is m by n is invertible. Okay, if the rank of A is equal to n. This we have seen in the last lecture. Another way to say this thing is that if A is invertible, if all the columns of A are linearly independent. And this fact is something that is related to the rank, as we said before. Okay, we say that A m by n is invertible if its determinant the determinant of A we denote with two bars. A is different from 0. Then, for example, if we want to check if the matrix A m by n is of full matrix, is of full rank, then we need just to calculate its determinant, and we need to find if this one is different from 0. And then it's like another kind of approach to understand if the rank of A is equal to n, then A is invertible. This is also due to the fact that we can define the inversion, the inverse matrix, with something related to the with the determinant, because I don't know if you know, but you can find on the internet for sure, on Google, that A inverse is like the adjoint matrix A that I've not explained, but is a matrix that depends on A divided by the determinant of A. But if determinant of A is equal to 0, then this one doesn't exist. Then the existence of the matrix is related to the determinant, but the determinant gives you some results, related to the rank, and the rank, is related to the invertibility of A. Then, everything is linked. And this is what I want to show in this page. Okay, now we can speak something about the idempotent matrix. The idempotent matrix A, that is m by n, is idempotent when is such that idempotent if A is equal to A multiplied by A. Usually we denote A by A squared. Remember that these are square matrices. And what happened here? Why it's important, the idempotent matrix? Because, for example, the matrix that is like that is an idempotent matrix and symmetric. This is a idempotent and symmetric. It's very easy to show that is idempotent, because if we try to, if this one we call A, and we want to do A by A, then we have X transpose X inverse, X transpose X transpose X inverse X transpose. And if X transpose X is invertible, and then the rank of X is K in the linear regression model, then this one and this one, we can cancel out, and then we get X transpose X inverse X transpose, that is A. And this is the proof that we have this matrix that is idempotent. There is a result that also is useful in regression analysis, is that if A m by n is idempotent, then the identity matrix with the n ones minus A is idempotent. Then it's very easy to find that In minus X transpose X inverse X transpose is symmetric and idempotent. Okay, well, I think that we have finished for this lecture, and thanks.